All right, we are live and recording. All right, so welcome students. I'm going to begin this Calculus 2 by getting into this section 6.1. Calc 2, we start off by working significantly with integrals. And we're going to look at some applications. In Calc 1, you would have learned how to do some basic integration. So we're going to look at more applications, and we're going to look at a lot of different types of integration techniques. Turns out that integration is typically a little harder than differentiation. So we'll spend quite a bit of time on that, really about half the semester we spent on integration. So to begin with, we're going to look at velocity and net change, or some things you would have talked about in Calc 1. Now, I wrote this over here. You can write this if you want to, but you don't have to. I just wanted to remind you of a couple of things. So in Calc 1, you learned that S sub t, that's the position function, okay? That's the position a particle is from the origin, right? That's S sub t. You also learned that if you do the velocity is a rate of change of position, so it's the first derivative. You also learned about antiderivatives, okay? So the idea is differentiation and integration are kind of reverse processes. So the idea would be is if you integrated this derivative, if you integrated s prime of t, well, you should get the velocity. Another way to look at that is how do you check the answer to an integral? Okay, well, you differentiate and see if that takes you back to the beginning. So what would happen on this is the answer to the integral of v of t is s of t. And remember, how do you check? You take the derivative, and that derivative takes you back to the beginning. Okay, so you want to think about that, make sure you understand that. So in general, we kind of look at it like this. The position is the definite integral from a to b. A and b are times. That's like a starting time, and that's a final time of v of t dt. So we're going to work with that formula quite a bit. We're just going in reverse, integrate the velocity to get the position. You'll find also when you integrate the acceleration, you get the velocity. So you're moving backwards. Okay, so here's kind of something I want to look at. This says, suppose you were driving along a straight highway and your position relative to the origin or a reference point is s of t for times that are positive, greater than or equal to 0. Your displacement over a time interval a to b is the change in position s of b minus s of a. So we're going to talk about this, and this says if s of b is greater than s of b, then your displacement is positive, and if s of b is less than s of a, your displacement's negative. So let's look at this diagram and talk a little bit about what this means then. Okay, so s equals 0, that's just your starting position. That could be the origin or it could be some reference point. A is a time. That's, maybe it's 1 second, 2 seconds, whatever, okay? B is another time, and B is greater than A, okay? So this is a later time than that, all right? So what happens is the displacement is just the difference in these function values, S of B minus S of A. So if you're going in a positive direction, then you should have a positive displacement, okay? So that's saying that that displacement, S of B minus S of A, is positive because you're going in a positive direction, okay? That's what that means, all right? The time B is bigger than A, and also S of B, in this case, S of B is greater than S of A. Now, it doesn't have to be that way, but it is if you're going in a positive direction like this, okay? So now let's look at this situation. Okay, again, the time is B and A. And again, B is a later time than A is. So what we're going to say is, here's time, this is time A, this is time B. Okay, and we're going this way now. That's kind of the key, is we're going this way. All right, so what happens is our displacement again is S of B minus S of A, but this time it's going to be negative. And the reason is because S of A is a bigger number than S of B. So you're going to get a negative displacement if you're going in the negative direction. Okay, whatever that is. Typically, if you're going to the right, that's the positive direction. If you're going to the left, that's a negative direction like that. All right, so the S of B, the displacement is S of B minus S of A, where B is a later time than time A is. Okay, that's the idea. Okay, so let's look down at this diagram. And talked about what this integral is, so it needs to make sense to you. If you integrate the velocity, that's the same as integrating the derivative of s prime of t, because s prime of t is the velocity. So if you integrate those things, those are equivalent to one another, okay? And what we also know is if you integrated a derivative, anytime you integrate a derivative, you should get the original function. So this just gives you s of t, and then remember, by the fundamental theorem of calculus, you just plug in the upper limit and the lower limit and subtract. Okay, so you're really getting the antiderivative, which is s of t, and evaluating it from a to b. On the integrals, you do s of b minus s of a. Okay, all these things you learned about in Calc 1, so you want to try to attach this to what we're doing with the integration. Okay, down here at the bottom, I want to go over this diagram just a little bit, and there's a couple of things that are probably worth writing down. So if the velocity, I'm going to abbreviate that, is a positive number, then basically what's happened is then you move in the positive direction. So I would recommend you write that down, kind of think about that. Okay, the opposite of that would be if the velocity is negative, then you are moving in the negative direction. Okay, and I'm going to use these diagrams to explain kind of what I mean by that then. All right, so you want to tie in everything you learned about, graphing and derivatives and integration in Calc 1. So this is the velocity function. This curve right here is the graph of the velocity. And this has function values. Right now, the value of the velocity is positive. Right in there, y'all have all those y values are above the x-axis. So that means right here you're moving in the positive direction. Okay, but when you get down here, all of the velocities are now negative. So what that's going to mean, from here to here, you are moving in the negative direction. So you want to be able to look at a graph of a velocity function and make sure you understand that. And right here, that would mean the velocity is 0. So that means temporarily you're not moving. So you're changing direction here. You're moving in the positive direction, and you're slowing down. The y values are getting smaller. Then you get to a velocity of 0. Then you change directions because you have negative velocities like that. So you want to understand that then, okay? All right, so the displacement is how far you are moving from respect to the starting point, and it can be negative or positive. It just depends. So remember, what we just learned is the displacement, s of t, is equal to the integral of v of t from some point a to b like that. And remember, an integral is an area under a curve. So what's happening here is you have this area here. That region there is going to give you a positive value. If you did the integral from a to here, you would get a positive a region represented by a positive number. The area is represented by a positive. But this is all below the x-axis, so from here to here, you would have negative. Okay, if you did that. So what happens then is on that, we would do A1 positive, and then you're really just adding a negative A2 to that. So that's why I say A1 minus A2. Positive region there, positive number represents area, negative represents area there. Okay, so that would be what the displacement is. So the displacement is really just the integral of the velocity from a to b, definite integral from here to here. But what would be happening is you would take this number and subtract this number because that's positive, because it's above the x-axis, that's negative because it's below. Okay, if it helps you, you're really doing A1 plus negative A2. A2 just happens to be a negative number. Okay, all right, so that's what we mean by displacement. Now, distance traveled is different from displacement, so you can write this down if you need to. Distance is always greater than or equal to 0. There's no such thing as a negative distance. There is such thing as a negative displacement. Distance is positive. So what happens here is when we find the distance, we're still doing the integral, but we're doing the integral of the absolute value of v of t that guarantees that both of these regions are above the x-axis. So you end up on this finding this area, and then adding them together. Okay, so this is giving you a positive answer. What you learned in Calc 1 is whenever the answer to a definite integral is negative, it just means you have more area below the x-axis than you do area above, and vice versa. Okay, all right, so this is all conceptual stuff on page 1. You want to think about these things and make sure you understand the connection between derivative and integral on these things. Now I'll go to the next page. Remember, on these videos, you can pause anytime you want to and review. All right, so let's take a look at this question here, and let's see kind of what we got going on here. So this says a policeman leaves the station on a north-south freeway at 9 a.m., so that's the beginning, and he's going north, that's the positive direction, for 40 miles between 9 and 10 a.m. Okay, so that's kind of the first part of the journey as we have that. And then from 10 to 11, he travels south to a point that's 20 miles south of the station. The station is going to be the beginning point then. So what I'm going to do is we're going to just draw a diagram, and we're going to answer a couple simple questions on this. So what I would suggest you do is just draw yourself a diagram. Just take an arrow and kind of draw like that. And what a couple of things I'm going to do on here, I'm going to just represent this as t equals 0. This is north, so that's the positive direction. This is south, so that's the negative direction. Now let's plot out what we have here. So from 9 a.m. to 10 a.m., I'll just put on here that's 9 a.m. At 10 a.m., somewhere up here, that would be time is 1 hour later. Well, what's happened? We have moved. I'm just going to put this over here. We have moved 40 miles. So I'm going to say right there, that displacement right there is 40 miles. Okay, so that takes care of that. Then what's going to happen is the next thing is from 10 to 11, he travels to a point that's 20 south of the station. So here's the station. Right there, that's where the station is. So that just means that you're going to go from here, turn directions, and go here. And this little piece right here is what we're going to find. But that we travel a distance of 40, not 40 miles, but we go 20 miles south of the station. So that part in blue is 40. Okay, this little piece here is going to be 20 south of that then. Okay. So here's basically what we do. The question on this is, what is the distance traveled? That's part A, is what's the distance traveled. Okay, so that's simple. The distance traveled, well, okay, you went 40 miles, then you went 20, you traveled to a point that is 20 miles south. Okay, so what that would end up being then is you would go 40 miles. Okay, then you went 40 miles backwards and then 20 more. So it's kind of what you're doing on this is you're doing that. So the distance traveled is going to be 100 miles. Okay, that's the total distance traveled. All right, it's the only way you're going to go 40 north, then you got to actually go 60 south to end up at that point right there. So you're actually going 60 miles south. Okay, all right. So that's part A, okay? And now the next thing what we would do on here is look at the displacement. So we're going to find the distance traveled and the displacement. So displacement's a little bit different. Displacement just means where are you in relation to the beginning. So you're actually just 20 south. So that displacement is negative 20. Well, so what do we do? So what we do is we do that initial displacement, 40, minus that 60 to get the negative 20. Okay, so that's how you find the displacement. So that's the difference between distance, you're just calculating positive 40 and positive 60. All right, because you're using the absolute value of those numbers. Displacement, you use the 40 north, so that's positive. You use the 60 south, that's why you do a negative. Okay, you can do that in your head, but that's what you'd end up doing. Okay, so what we get is the distance traveled is just the integral of the absolute value of v of t, and then the displacement is equal to the integral from a to b of v of t dt. Okay, so it goes like that, right? So pause and think about that a little bit and see if you understand that diagram. So I'm just using a diagram to help represent the north and south, and so you can kind of see where everything's going. Okay, so let's see. So now I'm going to kind of summarize the definitions that we did on here. So there's a few things I want you to write down. So we kind of went through the abstract part. So basically we have the position of an object denoted by S of t. That's something you learned in Calc 1. The velocity is the derivative of the position. So v of t is s prime of t. The displacement is given by an integral. All right, so you have a and b are times, and b is a time later than a. That's going to be this integral here. So displacement's the integral of velocity from time a to time b. And by the fundamental theorem of calculus, what this is really doing is just the antiderivative evaluated from the upper limit and bottom. Okay, that is just, like I say, that's fundamental theorem of calculus that you learn in Calc 1. Okay, then distance traveled. Okay, remember we get a positive number on this, so that just means that we're going to integrate the absolute value of velocity, and like on that previous page, that makes all the area be above the x-axis. Okay, so you don't get any negative answer on that, so that's the difference between the two. Okay? Okay, so let's just kind of fill this out and kind of summarize what we talked about. What is S of t? Okay, that is the position. That's not a bad idea. If you want to pause and just fill this out and see if you've got this down, then you can do that then if you want to. I'm going to just go ahead and move on here. So the position of the object at a time t, all right? V of t is the velocity of an object at a time t. Okay, a is the acceleration. That's the rate of change of the velocity. Not really talking about that yet. Of the object at time t. So those are the letters that we learned to use about this in Calc 1. Okay, so v of t is the rate of change of the object. So v of t is the derivative of s of t. So it's s prime of t. Acceleration is the rate of change of velocity. So there's two ways you could do this. You could write this as the derivative of the velocity, or it's the second derivative of the position. The velocity is the first derivative, therefore the acceleration, you do a derivative again, it's the second derivative. Okay, s of b minus s of a, well, that's the answer to this integral. So that gives the displacement of the object. Okay, so we want to make sure you know that formula right there, that integral. The displacement is given by the integral a to b of v of t dt. Okay, and that ultimately gives you s of b minus s of a. Antiderivative of v is s. The distance traveled, what's the difference? Okay, it's positive, so you got to do the absolute value of v of t dt. Okay, like that. All right, so that just gives you a positive number. All right. All right, so hopefully you kind of catching track on that, and you got this summary down. This is essentially, these are kind of the key things that you want to know. All right, so I'm going to move on to the next page. Pause if you need to. Okay, so now I'm going to kind of look at some of the types of problems that you'll do on homework a little bit to get us started. This is kind of a typical thing that you'll see on your homework. Okay, so let's read what we got going on here. So this says we have a graph shown in the figure. This gives the velocity of an object moving along a line. Assume the time is measured in hours, the distance is measured in miles. The areas of the three regions bounded by the velocity curve and the t-axis are given. So these are values of the areas of those different regions then. Now these are kind of diagrams when you're learning about definite integrals that you learned about. You use a positive number for these green regions, and you use a negative for that area that's below the t-axis, like that. Question 1, on what intervals is the object moving in the positive direction? Okay, so again, I said this a little bit earlier. You are moving in the positive direction when the velocity is strictly positive. Now that strictly positive is important, okay? If the velocity is 0, you're not moving at all, right? So what you're going to find on this is the velocity is positive in these regions here. So you see all of these values right here are positive. The velocity is positive there. Velocity is positive here. So you would have to name those intervals. So the intervals you would name would be from here to here and here to here. Now you got to be kind of careful about the way you name this interval. Okay, so starting at 0 to 1. Now we're going to go from 0 to 1. Okay, I write that a little clearer. Okay, so if we go from 0 to 1, we include 0. Why do we include 0? Well, because the velocity is greater than 0 right there. You have a positive velocity there. We exclude the 1. Why? Because the velocity is 0. Remember, you're moving in a positive direction if you have positive velocity, not 0 velocity. So that's how you write that. Then the next interval would be 3 to 5. So what do you think? Should we include the 3 and the 5 or exclude it? We exclude it. Okay, again, because the velocity is 0 at 3 and the velocity is 0 at 5. So the answer to that problem, you got to be careful about whether you include or exclude the endpoints. That's when we're moving in the positive direction. Okay, all right, so next thing is, question number 2 is, what's the displacement of the object over 0 to 3? Okay, so what we learned, we have the formula, is the displacement is the integral from 0 to 3 of the velocity dt. Okay, well, we don't know the velocity function, but we know everything we need to know on this. So what you would end up having on this then basically is from 0 to 3, you have an area that's use a positive number for 12, and then you use a negative number for 16 since it's below the t-axis, so you would have a negative 4 displacement. And what that means basically is that just means you're 4 units in the negative direction from the origin. Okay, that's you can have a negative displacement. Okay, so that's how you do that, real simple. Part C, what is the total distance traveled from 1 to 5? Okay, so when we do total distance, okay, then what we do is we're going to go from 1 to 5. We're going to integrate from 1 to 5, but distance is always a positive number, so we integrate the absolute value of the velocity dt like that. Okay, so let me just kind of erase, some of the marks I've made on this. So what we're doing here is we're going from 1 to 5. Okay, so what happens is the absolute value of the velocity, I would change that to an area above the curve. So what you really do on this is you just do the absolute value of that area, the negative 16, and then you do the absolute value of 10 too. So what you ultimately do on this is 16 plus 10 to get 26. You don't have to go through all those steps. You can do that in your head, but that's the idea on that problem then. Okay, you're getting positive, you're using positive values for those different regions. Okay. All right, next question is, what's the displacement of the object over 0, 5? So again, the displacement is an integral. So we're going to go from 0 to 5, and we're going to integrate the velocity v of t dt like this. Okay, so what's going to happen on this? Now, you don't have to write this down. I just want to mention this. You don't have to do the problem this way either, but I want to mention that really what you're doing is you're going from 0 to 1, v of dt. Then you're going from 1 to 3, v of t dt. Remember, you can break integrals up like this. Then you're going from 3 to 5, v of t dt. All right, so what we would have here is that would be 12 there. That's the value of that integral. The next integral, what is that? Right, that's negative 16. And the last one is 10. Okay, so you get 12 plus 10 is 22, minus 16 would be 6. Okay, so you get a positive value on that displacement. So that means that after you've gone from 0 to 5 seconds, you end up 6 miles away from where you started. That's what that means, okay? So that's the idea. Okay, so next thing I'm going to do is I'm going to, on this part E, I actually just answered the question on this. It says describe the position of the object relative to its initial position. That's what we just did, is this. So since it was a positive number, and the key is we got positive 6, that means that we are 6 miles on the positive side of the initial position. Okay, and then I'm going to do one more thing with this problem before I move on. I'm going to take that graph and kind of write a diagram that's kind of similar to the problem where we were going north-south, kind of like that. So I'm going to do that, and that'll kind of help you see what's going on. Okay, so watch this. Jot this down if you want to and see if this makes sense to you. Now, I could make this go north-south. This time I'm just going to make it go straight line, west-east like this. I'm going to say west is the negative direction and east is the positive direction. So here's what the meaning of this problem is here's time equals 0 seconds. Okay, when you get to 1 second, you've actually just displaced 12 miles. To the right, that's a positive number. So you've gone 12 miles like that. That would be after 1 second. Okay, then what happens from 1 to 3 seconds? Okay, 3 seconds, you're going to be going the opposite direction. So this is a negative 16. So you're going to go like that. Okay, so right now that green is 16 miles to the west. Okay, so right now you have a negative displacement when you do that then. Okay, and then that time over here is going to be, time is 3 seconds. Then the last thing you do is you go 10 to the right. Okay, so see right now, if you were 12 to the right, 16 to the left, this little piece right here ends up being a displacement of negative 4 then. So now you end up going from here, you go 10. So if you go 10 past negative 4, you end up at 6. Okay, so just think about that. You went right 12, left 16. So now you have a negative 4 displacement, and then negative 4 plus that 10 gives you 6. So when you get to time equals 5 seconds, you're actually just 6 to the right of where you started. Okay, and you started here. All right, so that's just a way to represent straight line motion like you're walking on a sidewalk or something. Okay? All right, so now I'm going to move to the next thing. Now we're going to actually start crunching out some integrals on this section now, and we're going to look at some graphs to kind of help us with some things too on here. Got to review trig. You should have dealt with trig plenty in Calc 1. So the first thing we're going to do is this, our velocity is represented by a sine wave on the interval 0 to 2 pi, just to make it simple. So we're going to graph the velocity function over that time interval, and then we're going to use that to determine when the motion is in the positive direction and negative direction. That's a typical thing we'll be doing. Okay, so I'm going to jot down a couple things on the side. You don't have to write these unless you feel like you need the review. So we have 10 sine 2t. So let's just use this as an opportunity to review a little bit. What is the amplitude? Okay, the amplitude is 10. And remember, it's the absolute value of that number in front. So what that means is the max and min stretches 10 units. Okay, so you would go up 10 and down 10, like that. Okay, the period. How do you find the period of a sine wave? The formula is 2 pi over omega, and omega is this number right here. That's the number in front of t. When you have a number in front of t, in the argument of the sine, you're changing the period. So that's 2 pi over 2. Therefore, that's equal to pi. Okay, and I'm going to show you how to graph this without a calculator, because you want to know that. Okay, you can check with your calculator, certainly, but you want to be able to do that okay and understand how the sine wave goes. So if we look at the increment of and I guess now we have a t-axis in this problem. Okay, what you do is you take the period and you divide this by 4. So the period is pi over 4. All right, so those are kind of the key things you want to know. You want to know the amplitude, the period, and then how to draw out your t-axis. All right, so what I'm going to have you do now is let's go ahead and let's construct a graph. Okay, so just kind of draw you a graph here. Okay, then we'll get this all set up. Okay, so the increment's pi over 4. That means what I'm going to have you do is count by pi over 4. You count like this. 1 pi over 4, and a lot of times I review real simple stuff because students need it. I just count like that. Okay, and eventually I'll get to, I need to make it all the way to 2 pi. All right, so let's do that. Let's get a good graph on here. So now we're at 2 pi over 4, so that's pi over 2. Then we're at 3 pi over 4. Then 4 pi over 4, which is pi. Now you just keep going. 5 pi over 4, 6 pi over 4, which reduces to 3 pi over 2. Okay, and then 7 pi over 4. And ultimately, you end up at 8 pi over 4, and 8 pi over 4 is 2 pi. Just want to remind you of how you can do that. Since the amplitude's 10, we want to make the v of t-axis go from negative 10 to 10. All right, and then here's how you graph this. Okay, so if you have a basic sine wave, if you're just graphing sine of t, it starts at the origin. There's no phase shift, there's no up-down, so you start there. Then the next point, you hit your max, which is 10, and then you just cycle through these points. Okay? Graphing calculator, I'll kind of remind you in a minute of how you want to put that in if you need that reminder. Okay, so that is our sine wave. Kind of like that. Okay, not very clean, but that's the idea. All right, so what we're going to do with this then is we're going to figure out when is the motion in the positive direction and when's it in the negative direction. So what you have to remember is positive direction if the velocity is positive. It has to be strictly greater than 0. Okay, so where does that happen? The velocity has positive values when you're above the t-axis. Okay, like that. All right. So what we would have then is we're going to be in the positive direction. Our interval will be this. Okay, so we're going to go from 0 to pi over 2, and we exclude those endpoints because the velocity is 0 at those endpoints. That doesn't count. You're not moving when the velocity is 0. Okay, then 0, then we're going to go from pi to 3 pi over 2. And then that would be the answer to where you're going in the positive direction. Okay. Negative direction just means when the velocity is negative. The value of the velocity is negative when the function values are below the t-axis. So the negative direction, you just write like this. That would be pi over 2 to pi, and then 3 pi over 2 to 2 pi. Okay, so that's what you got. All right, so what's happening right here is like if you were going north-south. Okay, you're going north. You're going back towards where you started, and you're going south, and you're going back towards where you started, then you're going north and south. Okay, if you're going east and west, if you're going east, back to the beginning, west, back to the beginning, and so forth. When you see a velocity function, you want to think about how the motion is going. That's real helpful to understand it at that level in that way. All right, so let's see. Next thing we're going to do is find the displacement over the given interval. Okay, so we know the displacement would be the integral all the way from 0 to 2 pi of v of t dt. So that would be the integral from 0 to 2 pi of, and our function is sine of t dt, of 2t dt. So that's what we got to work out. Now we're going to go ahead and work it out. If you understand how this function works, you could tell me in your head what the answer is going to be, okay? And I would like you to be able to know what the answer is on that. So I'm going to need to erase this stuff right here so I can kind of take a little bit of room up and just kind of review a lot of things. I like to kind of review as I go because you're going to forget things you learned from Calc 1. So first of all, a couple of things to remember are these two things. So the integral of the sine of t dt, what do you take a derivative of that gives you a sine? Yeah, negative cosine t dt. Okay, that's important. The other thing that's important to remember is the integral of the cosine is the sine. That's one thing you want to do is review your basic integral rules you learned in Calc 1 and your basic derivative rules like that. Okay, well, you can take a shortcut. You don't have to do u substitution to do this. So I think it's real helpful if you learn, if you're doing the, there's kind of a general formula for if you do sine of at, where a is a constant, well, then that just ends up being 1 over a, and it's still negative cosine of at, okay? And so we're going to get that antiderivative that way then. Same thing happens on the cosine. If you did the integral of cosine at dt, that ends up being 1 over a sine of at. And you want to kind of convince yourself in your mind why that works, okay? The reason this works is because if you take the derivative of this, 1 over a times negative cosine at, you'll end up getting the sine of at. I'll just go ahead and show you that. So you do a derivative. 1 over a is a constant, so you just write it down. Negative is a constant, and the derivative of a cosine, remember, is negative sine of at, and by the chain rule, the derivative of at is a. What that does is it crosses out the a's, you have a negative sign, so you're back to the beginning. Okay, so I would highly recommend, if you don't know this formula, this integral formula, when you have a constant on a trig function, that you know how to handle that. Otherwise, you got to do u substitution, or you can reason it out in your head too pretty well. All right, well, we're going to go ahead and crunch this thing out, even though you may know what the answer is. So the antiderivative of the sine of 2t is going to be 1 over 2 times negative cosine of 2t by the formula we went through, like that. And you know what? I missed the 10. I just realized I missed that 10 right there. So I got to put that in like that. Okay. All right. So what you could do is you can bring the 10 out. So you would end up having 10 times the integral 0 to 2 pi of sine of 2t dt like that. Okay. You can remember you can bring constants out of an integral if it's multiplied by the function. So now what we have is 10 times, now the antiderivative is 1 over 2 times negative cosine of 2t, and we're going to evaluate that from 0 to 2 pi. So we're going to get into some unit circle stuff too. All right, so I'm going to erase all this stuff so I have a little bit of room here, and then we're going to close this out. Okay, so we're going to move this over here. So what we'd have is 10 over 2 is 5. So that's going to give us 5, and it's a negative 5. Okay, after we cancel that out. So it's negative 5 cosine of 2t evaluated from 0 to 2 pi. Okay, like that. All right, so let's see what we got then. All right, so negative 5 is a constant, so just write it down. And then we're doing fundamental theorem of calculus, so we do cosine of 2 times 2 pi minus cosine of 2 times 0. Like that, work it out. So we have negative 5 cosine of 4 pi minus cosine of 0. And we can work that out. Okay, unit circle time. 4 pi is 2 laps around the circle. That's at the point 1, 0. The cosine is the x value. So we would have, for 4 pi, you would end up there at negative 5. Cosine of 4 pi is 1. Well, these angles are coterminal, so 0, the cosine of 0 is also 1. So what you get is negative 5 times 0, so you get a displacement of 0. All right, so the answer to this problem is 0. Now, I hope that doesn't surprise you. You can tell by the symmetry of this graph that what happens is this. That region, that integral from 0 to 2 pi over 2 gives you a positive value, okay? Then you'd have a negative, then a positive, a negative. They all just kind of cancel each other out. So you could look at that and know that. If you know that about the symmetry, then you can easily figure that one out in your head without having to do anything, okay? All right, so one other thing that we want to do next here is we want to find the distance traveled from 0 to 2 pi. So when we do the distance traveled, okay, what we're supposed to do on this is the formula is we're going to do the integral from 0 to 2 pi of the absolute value of the velocity. So we're going to do the absolute value of sine of 10 sine of 2t dt. All right, now what you have to do on this now, you have to kind of take advantage of the symmetry here and everything, okay? So thing about this is what happens is these regions are all symmetrical here. Okay, so those are giving you positive values, and these things right here are giving negative values. There's 4 regions. So what you can do is you can just break this up like this. Okay, you can say, okay, we're just going to do, well, we know this area right here. We know that's positive, and we know how to integrate just positive 10 sine 2t. So we're going to say 4 times the integral from 0 to pi over 2. And then we're going to do 10 sine 2t dt. That's what we're going to work out. Now, understand on this, all I'm doing is I'm just looking at this region right here. I'm just looking at that region right there and quadrupling it. Because we're really what happens on this problem is absolute value. It just changes that region, flips it over the t-axis on that one too. So that's really what you're integrating is that. Okay. All right, so that's what we're going to do then, and this one will be pretty simple to work out, so I'm going to go ahead and work this one out. Okay, 10 is a constant. You can bring it out. So we would end up having 4 times 10, or 40, times the integral from 0 to pi over 2 of sine of 2t dt. Like that. Okay, we're going to use our formula, 40. The antiderivative of sine is negative cosine. But you have that constant, so it will be 1 over 2 times negative cosine of 2t, evaluated from 0 to pi over 2. Okay, like that. All right. So what we're going to have then is this will be 40 over 2 is 20, so that's just going to be negative 20 times the cosine of 2t, evaluated from 0 to pi over 2. So now we're ready to, we have our antiderivative, we're ready to evaluate it. So just write down the negative 20, upper limit goes in, you'll have cosine of 2 times pi over 2 minus cosine of 2 times 0. And that will be negative 20 times cosine of pi, the 2's cross out. And then cosine of 0, like that. And you can look this up on the unit circle. Okay, it's kind of like this. Pi is there. Okay, so halfway around the circle's pi. That's the point -1, 0. The cosine's the x value, so that would be -20 times -1. 0 is at the point 1, 0. The cosine is 1, so it's -1. So you end up with -20 times -2. Therefore, the answer to that problem is 40. So the total distance traveled is 40. Okay, so what I did is I did really each little hump on this graph is 10. We just quadrupled it. So a lot of times you have to break these integrals up because there's not really a formula for the integral of an absolute value of a sine of 2t. You know how to do integral of sine 2t, but not necessarily the absolute value. Okay. All right, so I want to do one other thing. I want to remind you a little bit on your calculator, and I'm hoping you're fairly familiar with this from Calc 1 because your calculator will help you to understand, check answers. It does all kinds of good things for you. And you're going to, in this class, you guys will be able to use calculator on test. So you're going to have the ability to numerically check some things. And when you're doing definite integrals, you got that power. So you want to take advantage of that power. So let me show you a couple things. Okay, first of all, let's put in, you want to be in radian mode. If you got your calculator, do this with me. You always want to be in radian mode when you're working with trig functions. Press y equals, and then just put in 10 sine, and just put in 2x. Okay, like that. And then we're going to be going from 0 to 2 pi. So for your window, just put in the x minimum 0, and the x maximum is 2 pi. Sometimes you want to go a little bit bigger. I'm just going to stop it at 2 pi. And then we can scale that by whatever we want to. I'm going to scale it by pi over 4, because when we graphed it, whoops, not e, that has nothing to do with the problem. So pi over 4 was our increment. Okay, so that's the scale I'm going to use. Okay, and let's see, -10 to 10 is good because of the amplitude. Okay, so one of the things I can do with this fancy calculator, I can kind of go over here at the side and I can put these things over there so you can refer to them if you want to. Okay, so a graph. Okay, this gives the graph. And then I want to kind of talk through a couple of things that we did on this then. All right, so if you want to check the answer to part B, what you do is you just go second, trace, option 7. If this is new to you, this is a great thing to learn. Hopefully you learn this Calc 1. Do that. The lower limit is 0, because remember we were integrating from 0 to 2 pi. Put that in. It'll shade, and it'll give you an answer. Whoops. Oh, what did I do? I'll do something wrong here. Hold on. Let me start over again. I don't know what I did wrong. Okay, so let me try again. So second calc, option 7, lower limit is 0, upper limit is 2 pi. Sometimes if you don't go beyond the limit, it won't do it right. Yeah, that's what it is. So let me show you what happens. This will happen sometimes because 2 pi is an irrational number. 0 is okay. That's a rational number. So what you need to do on your window is you need to do this. Then it'll work. And this is kind of an important thing to make a note of. So instead of going to 2 pi, let's just go to 3 pi. Okay, and then put that in, then graph. It just takes the graph out a little further. Like that. I don't know what happened to all the stuff I was writing down. There it goes. Okay, so let's try again now. So let's go second, trace, option 7, integrate lower limit 0, upper limit 2 pi. And 2 pi is an irrational number, so the calculator doesn't know how to handle it. Okay, it'll shade that in and it gives you 0. Now you have to understand this too. That's scientific notation. Your calculator is doing this numerically. That's close to 0. I mean, that's a 6.09 with decimals to the left 13 places. So it's a number that's close to 0. 0 is the exact answer. So you can use that to check. Okay. And then that's the idea. You can also do this. This is worth trying. The absolute value function you find in math, number, ABS, and then you could put in 10 sine 2t. Now what that's going to do, this graph, when I put this in, it's just going to move all the humps up above the x-axis. And then if you wanted to check the distance traveled, then you would just do the same thing. Second trace, option 7, lower limit 0, upper limit 2 pi. Okay, shades it in, gives you 40. Okay, so see, that thing could be done on a calculator. You want to know how to do both. You got to know how to do it by hand. You got to know how to do it by your calculator. You know, those of you, a lot of you are going to be engineers. Yeah, you're going to be doing a lot of things numerically. But you're learning calculus, so you want to learn the concept. So we want to learn how to do both. Okay, so got a few more things we want to talk about then. So I'm going to move on to the next page. Okay, so I'm going to develop a formula for you here. So the idea with this is this says, suppose we know the velocity of an object at its initial position s of 0. The goal is to find s of t at some future time. So we're looking at times that are positive, 0 and above. And time's always positive, 0 or a positive number. The fundamental theorem of calculus gives the answer directly because the position is the antiderivative of the velocity. So I want to go over this formula and just kind of talk through this. All right, so what we're going to do is ultimately we're trying to find s of t. We're trying to find s of t from the velocity. So like we learned, if you integrate the velocity, you're going to get s of t, okay? So the integral of the velocity is the same as the integral of s prime of t because v of x is the same as s prime of x. So therefore, you're just integrating the same function, okay? The antiderivative of s prime is s. So the antiderivative of s prime is s. We evaluate from t to 0, plug in the upper limit to get s of t, subtract the lower limit like this. So what you end up having is you have the position function evaluated from 0 to t is the same as s of t minus s of 0. Okay, however, this thing right here is the same as this. So what I'm going to do is just replace that with the integral from 0 to t of v of x dx. And we just figured out that that's equal to s of t minus s of 0. So what we do is we have an equation. This equation can be solved for s of t because that's what we're trying to find. So you could add s of 0 to both sides. Then you would get s of t, like this. You would just end up with s of t equals s of 0 plus that integral 0 to t v of x dx. So that's what this formula is, and that's where that comes from. So the position function at a time t is the same as the initial position plus the displacement over that time unit from 0 to t. Okay, that's where that comes from, just applying some of the basic things that we talked about. Okay, so let's move down the bottom. And I'm going to do a graph on this. I'm going to go ahead and put this on the calculator because I want to do a little bit of checking probably on this thing too. So if you have your calculator, go ahead and just do this with me. Erase this and put in this function. So we have x to the third and minus 5x to the second and plus 6x. Okay, like that. And we're going to graph on the interval 0 to 5. Okay, so that's what I've got in my calculator. And let's set up a good viewing window. So window, we know we're going 0 to 5. You don't have to go past 5. 5 is a rational number. Anytime you have the endpoint of pi or an irrational number, you got to make the calculator go out a little further. Let's just increment that, scale that by 1. And then to get the y, just look at your table of values is what I do. I just go second graph, look at my table of values. So notice between 0 and 5, the y values vary from 0 to 30. So 0 to 30, and you may even have a few negative values in there. It's hard to tell. So I'm going to go ahead and just do this then, just to be safe. I'm going to go negative 10 to 30, or maybe even 40 by a scale of 10. Just to be safe and make sure we can see everything. So I'm going to use that viewing window, and I'll go ahead and graph that out. Okay, so I end up getting this thing right here. So what I want you to do is just sketch a graph, and label this as 0, 1, 2, 3, 4, 5. So that's the t-axis. And then on this is just 10, 20, 30, and that's good enough like that. So that's our graph. You can use a graphing calculator to get this, all right? So again, we're going to do the same thing we've been doing. Determine when the motion's in the positive direction and when it's in the negative direction, okay? So positive direction, okay, what did we learn? That's when the velocity is what kind of number? Greater than 0. Okay, where does that happen? That happens basically here. You have positive velocities there, and you have positive velocities there. Okay, the graphing calculator kind of shows you where these zeros are. I'll show you algebraically how to do that in just a minute. So anyway, what you would have is, okay, the velocity is 0 at all of these points except 5. So carefully you would write this interval 0 to 2, parentheses, then you'd have a 3 with parentheses. Now let me ask you this question. About the 5, should y'all use parentheses or bracket? Bracket, because the velocity is 30. The velocity is a positive number, so we include that. So we would be moving in the positive direction, okay? Part B would be when are we moving in the negative direction, okay? What we learned is this happens when the velocity is negative. So that would happen here from 2 to 3. Okay, so that answer would be 2 to 3. Again, you would use parentheses on that. So make sure you understand the distinction between parentheses and bracket in that ratio, or in that interval, I'm sorry. So, by the way you can find these zeros is, your graphing calculator will help you with this. You don't always want to go by looks, but if you take this function and set it equal to 0 and solve this equation by factoring, you're going to get these zeros. So I'm just going to review this real quick. Factor out of t, you'd have t squared minus 5t plus 6. This is a trinomial that factors. This factors as t minus 2, t minus 3 equals 0. So you get t is 0, which represents that point. T equals 2, which is this point. And t is equal to 3. Okay, so if you need to find those intercepts, that's how you would do that algebraically. Calculator shows you that pretty clearly on that problem. Okay, so let's move to the next page here. Okay, still working with that same function. Okay, so you just got to know how to set up your formula. So we're going to find the displacement from 0 to 5. Okay, so the displacement we learned is the integral of v of t dt. In this case, we're going to go 0 to 5. Okay. All right, so when we put this together, that's the integral 0 to 5 of, and our function was what? T to the third minus 5t to the second plus 6t times dt. Okay, so we're going to do this. This would be an example of an integral that's a calculus 1 level integral. It's basic power rule. So just a quick, what did I just do? Okay, so a quick reminder on here is the integral of like t to the n dt. The power rule is t to the n plus 1 over n plus 1 plus c. Hopefully you got that down real easily. So the integral of t to the third is t to the fourth over 4 by the power rule. The next one would be 5 as a constant, and then that would be t to the third over 3. And then the integral of 6t, the constant, just write it down, that would be t to the second over 2. And then we're going to evaluate that from 0 to 5. Okay, so that's kind of what you would have done in a Calc 1 class. You can just put that all together like this. Okay, let's see, we can simplify. This thing right here would become 3. So I'm going to write this down one more time. So I'm going to just write this down as t to the fourth over 4 minus 5t to the third over 3. You can also write that as 5/3 plus 3t to the second from 0 to 5. Okay, now we're going to do arithmetic. All right, so we're going to plug in the 5. So we'll have 5 to the fourth over 4 minus 5 times 5 to the third over 3, plus 3 times 5 to the second. Okay, and then we'll have minus and then plug in the zeros. Now you can do this in your head. You know, I like to try to teach pretty detailed, but you know, if there's things that you see, you can always move ahead a little bit in my video. But just the reason I'm taking the time to do that is this whole thing's going to be 0. Well, most of the time when you get practice, you start doing that in your head. So that whole thing right there doesn't make any difference. That's just 0. Okay, so when we work this out, what we're going to have is 5 to the fourth, which is 625 over 4. 5 to the third is 125. Okay, and then that really is 5 to the fourth, so that's 625 again. So this is 625 over 3. And then this is 25 times 3, so that's 75. So I'm just going to get common denominators on this. I'm going to put this over 1. I'm going to remind you how you can do this on the calculator also. Common denominator of 12. Multiply that by 3 over 3. Multiply this by 4 over 4. Multiply this by 12 over 12. You get into big numbers, so you want to use your calculator on this. Okay, so let's see. Numerically, I'm just going to do this. 625 times 3. It's going to give 1875 over 12 minus, and then if we do 625 times 4, you can do stuff in your head, just do it in your head. We're in a world where we kind of get lazy about stuff like that now. And then 75 times 12 is 900 over 12. Okay, then you can put it all together. So we have 1875 minus 2500 plus 900. So that gives 275. I think I did that right. So that is, hold on just a second. No, I'm okay. I thought I saw a mistake, but I'm fine. We're going to check on the calculator here in a minute anyway. So 275 over 12. And then once you do that, that fraction, I don't think that reduces. Okay. Now, so that would end up being our displacement. That would be the answer to part B. Okay. A couple of things too. You don't always have to do stuff by hand this way. I mean, you could go like this. If you could actually just go 625 over 4. I'm just back at this point right here without getting a common denominator. Then you could say minus 625 over 3. And then you could say plus 75. Okay, like that. That'll give you decimal. Now, we want exact answers typically. So you can go math, fraction, press enter, and it gives you that answer. Okay, so you can do your fractions numerically. If you don't know that, man, you need to know how to do that. Sometimes students, depends on who they've been taught by, but you want to know how to use your technology really good. Because if you're engineering major science, you're going to use technology, okay, all the time. Okay, so that takes care of that. Just kind of a quick reminder on this graph. When we did this displacement, you can check it this way. You can do it super easy this way. You can go second, trace, option 7, integrate from 0, lower limit of 0, upper limit of 5. It'll shade that in, and then that gives you the same, that gives you the decimal answer to what we had then. So that's the idea. Okay. Okay. All right. So anytime you need pause the video and process stuff, do that. That's a good thing about being in an online class is you could do that with these videos I give, right? So in my regular classes, I give videos too that you can view outside of class. So this is great. I wish I had this when I was a student. My God, it would have helped me. All right. So let's see. One additional thing on this page. So the next thing I'm going to do is we're going to find the distance traveled, and we're going to kind of talk about how that's going to go then, all right? Okay, I'll probably have to erase this, so pause now if you need to write this down, but I'm going to go ahead and erase this. Calc 2, the problems get a little long. I like to try to write down every step that I can, so you don't miss anything here. Okay, so the next part of this is find the distance traveled. So what's the difference? The distance traveled, what you're going to end up doing is you're going to do the integral from 0 to 5 of the absolute value of v of t dt. Okay, so we need to kind of go back and look at the graph. There's several ways you can do this, and I'm going to do this numerically. I'm not going to work out the integral, and I don't always in this class take time to work out the arithmetic part of integrals, but really what's happening on this graph, if you look back at this graph here, this region is positive. That will have a positive value from 0 to 2. So you could break it up like this. You could go integral from 0 to 2 of the velocity function, which is t cubed minus 5t squared plus 6t dt. And we're going to do that numerically on the calculator. Okay, I'm not going to take the time to do that. There's no sense in doing that. And then you've got negative. That region is below the curve. So what we're going to do on that is we're going to do the integral from 2 to 3 of the velocity function. Okay, and then the last part goes back to positive, so we're going to integrate from 3 to 5 of that velocity function. And this we're going to do numerically. All right, since we got this all graphed on the calculator, then this is really all you need to do here. Okay, and so what I'm going to do is I've got my graph here. I'm going to go ahead and go second trace, option 7, and we're going to integrate from 0 to 2. So lower limit 0, upper limit 2. Okay, and I'm just going to write down decimals, and what you want to do is you want to use as many decimals as you can on here. So clearly that's just repeating 6s, okay, like that. And we're doing absolute value. I mean, that's a positive number, so it doesn't matter. It's the next one that matters. So I'm going to start over again. I'm going to do option 7. Now I'm going to integrate from 2 to 3. So lower limit 2, upper limit 3. That gives a negative. So this is where you have to do the absolute value, 0.41. And then again, that's repeating 6s. Just use all those decimals when you do that then. And then finally, the last thing we're going to do is integrate from 3 to 5. So I had that integral here from right here, 3 to 5. So option 7, start at 3, go to 5, and record that, okay? And just for emphasis, I'll put in the absolute value function like that. Okay, so that's what we have. I'm going to quit, clear the screen. I'm just going to put this in like this, okay? And the more decimals you put in, the more likely it'll change this to a fraction for you. Okay, so I'm going to put that in. This I'm going to use a positive number now, so 0.416, put a bunch of 6s in there, like that. And then plus 20.6, put a bunch of 6s in like that. This is how you can do this problem numerically. Now, it may or may not change this to a fraction. So I can go math fraction. I didn't do it that way. I was afraid of that, but you could, if I was looking for a numerical estimation, then you could just say 23.75. Now, for all practical purposes, I'm pretty sure that's probably what it is. So if we do 23.75 and then do math fraction, 95 over 4 is what you get. Okay, so the exact answer on this, I worked that out earlier, is 95 over 4. Okay. All right, so let's see. I was going to just kind of write down a couple of things on this. Actually, what happens, if you work out these integrals numerically, this thing turns out to be 8/3. The second integral turns out to be -5/12. You could change these things individually to fractions. I think that's what I did. And then that third integral was 62 over 3. And then you could put that in your calculator to get, you'd end up getting 95 over 4. Okay, like that. And anytime you got repeating decimals, the calculator will usually convert it to a fraction if you put several decimals in it. Okay. Okay, so that kind of takes care of that. So we've kind of got that established pretty well now, hopefully. Okay, so now we're going to move down to example 4, and we're going to determine this position function. So we're going to do one thing a little bit different on this problem, and then that'll kind of get us close to being wrapped up here, I think. Okay, so I went ahead and just graphed this on the graphing calculator. So let's see, that's a quadratic function, and I'm basically on this, I'm just going from 0 to 4, and this was negative 10 to 10 is how I scaled that on the calculator. You should know that that's parabola pointing down, moved up 9, okay? All right, so again, the same kind of stuff. I'm going to just kind of quickly go over this. Okay, positive direction, what are you looking for when the velocity is greater than 0? So the positive direction is going to be there to there. Okay, so that's going to be bracket 0, 3 parentheses, like that. Okay, the way you find that 3 too is you just say 9 minus t squared equals 0. Solve this equation. Okay, so you get t is plus or minus 3, so clearly that's a 3. Okay, and then the negative direction, what did we learn? That's where the velocity takes on negative values, so that would be 3 to 4. So exclude the 3, but include the 4 because you do have a negative value at 4. Okay, so that's that again. I don't want to do that anymore. Okay, so next thing is we're going to determine the position function for t greater than 0 using both the antiderivative and the fundamental theorem of calculus for agreement between the two methods. All right, so once we got that graph put together, so what I want to kind of go ahead and do is write down kind of the conditions we have here. This is a problem you actually sort of learned how to do this in Calc 1. So what we have is we know that S of t is going to be the integral of 9 minus t squared dt. And then what we also know on there is we know this initial condition, S of 0 is equal to negative 2. So I'm actually going to show you 2 ways to do this problem. One by the theorem, the formula. The other, by the way, you learned how to do this in Calc 1. Now, we're not integrating from 0 to 4. We're not finding like the area under the curve. We're finding a function. We're not finding a numeric value, so we're not going to 0 to 4. Okay, so let's go do this like this. So this is an indefinite integral. So if you did this, this would be, the antiderivative would be 9t minus t to the third over 3 plus c. Okay, so that's what S of t is, but this initial condition right here, that allows us to find c. So this is just giving you a point, 0, negative 2. That's t, this is S of t. Okay, so you just plug in. So S of t goes here. Everywhere you see a t, you put in a 0. So you'd have 9 times 0 minus 0 cubed over 3 plus c. Well, okay, all that goes to 0, so that just means c is negative 2. So that means the answer to the problem would be this thing, but you tack on the 2. So you would get S of t is equal to 9t minus t to the third over 3 minus 2. So that would be your function using that method. And that should look familiar to you from Calc 1. We usually teach how to do antiderivatives, and initial conditions can be used to find the value of c. So that's how that goes. Okay, now here's the second way to do this. Okay, the second way is to use this formula. Most of the time I don't use this formula. I just do it like this. I just find it just as easy to do that way. So let's see. So the formula we're going to use is this one. And we talked about this a little bit earlier. So you can build a position function by doing this. That is the initial value And then this is, the integral doing the antiderivative, okay, like this. All right, so let's put this together. Okay, what is S of 0? S of 0 is -2. I gave that to you. All right, now if we do this integral, what we're doing now is we're going to do the integral from 0 to t. The velocity function, again, is 9 minus t squared dt. Okay, or I'm sorry, x. We're doing this in terms of x, and then we're going to translate that into the variable t. X is kind of an intermediate variable. Okay, so I go like that, right? So what I'll have, this is -2. Antiderivative is 9x minus x to the third over 3, evaluated from 0 to t. And then there's hardly much more to do. We'll get the same answer. See, that -2 gave you c. That's kind of what that turned out to be. So this would be -2. Now evaluate, plug in the t, you would have 9t minus t to the third over 3 minus, plug in the 0, so it would be 9 times 0 minus 0 cubed over 3, like that. So that's what you work out. That crosses out. You would get -2 plus 9t minus t to the third over 3 is equal to S of t. Same answer. Okay, just written in a different order. So you can do that either way. Like I said, I find it just as easy to do it this way. Just because the initial condition allows you to find the arbitrary constant c. That's the idea. Okay, let's see. So graph the position function. So basically what I did on this, and I want to show you something on this too. I want to see if you can make kind of a connection on this. So if you put this position function in your calculator, I'm going to put that in. So our answer was -2 plus 9t minus x to the third over 3. And let's see, we're just going to graph this like this. For a window, I'm going to go just 0 to 5. And I think what I'm going to do on this is -10 to 20. I'm going to try that like this and see if this works okay. And I'll slide that over there just, for reference, if it'll move over there. There it goes. Okay, so I'm going to graph. So I end up getting that. All right, so what I want to do on this is I want to look at two things here. That's what the graph looks like. So if you want to write this down, that's just going to 5, that's going to 20, and that's going to -10. And this is the graph of S of t. So I want to compare this to the velocity. So I'm going to move this over here for a second. Then I'm going to go back and just quickly, I'm going to put in the 9 minus x squared. Okay. All right, so I got 9 minus x squared. Okay, this was the velocity function. I'll do this in the same window, and that's good enough. Okay, now I want you to watch this. You don't necessarily have to write this down unless you really, really want to. Okay, so here's the idea. This is S of t. This is v of t. Okay, so there's a relationship that goes on here. Remember that the velocity is the derivative of S of t. So what is a derivative? Derivative is a tangent line. It's a slope of a tangent line. So what's going to happen on this is the velocity, the tangent line right here, is positive. Right now you have positive derivatives until you get to the maximum and you have a 0 derivative. Then the derivative, the tangent line, starts sloping downward. So I want you to realize on here, see, the velocity has positive values here. The velocity is 0, where it would be there. Okay, it would be at 3 seconds. Then you start having negative velocities. So what's happening on this position function is you're basically have positive values, and what's happening on that is the slope of the tangent line is getting smaller. So you're slowing down. You have a pretty big velocity there, but it gets smaller until we get to 0. That's what's happening. You start with a big velocity, get smaller until you get to 0. And then negative velocity just means you're changing direction. Okay, so that's what's happening on that problem. Okay, So those are good things to think about, is the graphical relationship between S of t and V of t. Back when I was a student, when calculus would be back in the 1980s, we didn't have graphing calculators. We didn't really talk about that stuff very much. I think we do a much better job now of looking at graphs and the meaning of derivatives, because I think technology helps us to do that quite a bit. Okay, so let's see. Going to wrap up here with just a couple other things. Okay, so let's move to this example 5. We're going to run through this and then one last example to wrap this up. So this problem, what this is saying is flying into a headwind, the velocity in miles per hour of an airplane flying into a headwind is given by this velocity function 0 to 3. And then here's this initial condition. Now, what we're going to do on this is kind of what we did on the last problem. We're going to determine and graph the position function. So you can either do the formula right here. You could use this formula if you want to. You can certainly do that if you want to, or you can just do it the other way. I don't really care which way you do that. I'm going to go ahead and just do this using the formula. I'm going to go ahead and write this down. So I have S of t is built by taking the initial value, which you're given, plus the integral from 0 to t of v of x dx. Okay, so this should be a pretty simple integral. The integrals in this section aren't too bad because we're just using the types of integrals that you learned in Calc 1. Okay, so according to this, S of 0 is 0. That was given. So that's a given. Then we have the integral from 0 to t of this function, which is 30, 16 minus t to the second times dx. Okay, you got to be kind of careful where you do x as an intermediate variable. So I write this like this, 16 minus x to the second times dx. Okay, so let's work that out. So you can bring the 30 out. The 0 doesn't have any bearing anymore, so we have 30 times the integral 0 to t of 16 minus x squared dx. I'll move this over here. So that's 30. The antiderivative of 16 is 16x. The antiderivative of x squared is x to the third over 3 by the power rule. Then we're moving from 0 to t. Okay, then we're ready to evaluate this. So we have the 30. And it goes like this. Okay, the first thing we'd have is 16 times t, just plugging in the t now, minus t to the third over 3. Then plug in the 0, and you can bypass this because you know what's going to happen. You like it when you have a 0 in your limit of integration. Okay, so we end up evaluating that way. That goes to 0, so it looks like what you'll have is S of t is this. Okay, so that looks like that is 30 times 16t minus x to the third over 3. And you don't have to worry about the plus c because we already figured that out in that formula then. Okay, and then we can multiply that out if you want to do that then. So I'm going to go ahead and do that and just write it in a multiplied out formula form. Okay, so that would be 480. I don't need a calculator. God, I'm getting lazy. So that's 480t. 30 over 3 is 10. That reduces out, so you end up getting this answer. Now, it's t's. Get a little careless here. Okay, so I think I got everything fixed. So the final answer would be 480t minus 10t to the third would be your S of t. That's your function. Okay, if you multiplied it out, you would have that form. Okay, now we're going to graph that on the calculator. Okay, and just because we're going to do a little bit of work on the next page, a few different things we're going to do with this particular function. So I'm going to go ahead and put this in. 480 times x minus 10x to the third Okay, if you read the problem said, I think you're interested in the interval 0 to 3, so the x is going to go 0 to 3. So the window, we're going to go 0 to 3. And again, for the y, this is what I do. I just go second graph, and I just look at the y values. Okay, 0, when you get to 3, you're at 1170. Okay, so I'm going to go up to like 1200 or 1500. Let's go all the way to 1500. So for the y's, let's go 0 to 1500, and then maybe scale that by 500. Okay, and then that'll give a graph. Okay, I didn't scale that right though, so it needs to be a 500. It looks a little bit better if I do it this way. Okay, so that would be my viewing window. All right, and then the graph goes like this, and I'm just going to move that to the side, just kind of for reference. Okay, so in this particular problem, this is the graph. If you want to sketch this down, you can. This is S of t is equal to 480t minus t to the third. And then this is the time axis going up to 3. And then this is S of t going by 500. Okay, so you can write that down if you want to, but you don't have to. I just mainly want to have this to kind of refer to in the next problem here. Okay, all right, so that's kind of what we have here. That's real bright. Okay, now all my scribblings kind of moved, didn't they? All right, so let's see what this next problem says then. Okay, so that goes to 3, that goes up to 1500. This is S of t. All right, that's the key step. So how far does the airplane travel in the first 2 hours? Okay, so what that is talking about is that's finding the displacement at 2 hours. Okay, so we already know what S of t is. We figured out that S of t is this function up here, 480t minus 10t to the third, so we just need to find what S of 2 is. Okay, remember, we have the displacement function, so we're just evaluating it. Okay, we're not integrating or anything. We were integrating the velocity to find S of t earlier. So you just plug this in, crunch that out on the calculator, and do that. So, okay, so I'm just going to put this all in my calculator, be lazy. Okay, so let's see, I got 480 times 2 was what, 960. This thing right here is 2 to the third's 8. 8 times 2 is 8 times 10 is 80. So that would end up giving you 880 miles. All right, so that is the displacement. All right, now what that represents is that just represents this point. Okay, 2 seconds, you have displaced 880, so that's a point that's on the graph. Okay. All right, next thing we're going to look at is how far has the airplane traveled at the instant of time its velocity reaches 400. Okay, now this problem you got to do quite a bit of work on. All right, so what we have is first of all, I'm going to write down that function S of t is 480t minus 10t to the third. Now what we got to do is we're going to find how far has the plane traveled when the velocity reaches this. So that means that what we got to do is we got to find the velocity. Okay, all right, and what we got to do is find that velocity function then. All right. So what I'm going to do is the way we find the velocity is we do the derivative. We do s prime of t, so let's go ahead and do that. That derivative would be 480 minus 30t to the second. Okay, so that's what we'd have. Now what we're going to do is find how far the plane traveled at the instant that the velocity was 400. Okay, so here's what we got to do. That velocity is given as 400, so we're going to have an equation that will allow us to figure out what the time is. Okay, we got to find the instant when the velocity reaches that. So that's kind of step one. Step two, we're going to solve this equation. So we have 400 is equal to 480 minus 30t to the second. Luckily, this is a quadratic equation, but we can use the square root property on this. So I'm just going to kind of rearrange things. So I'm going to move the 30t so we get this. I'm going to move the 400. So I'm just, isolating the variable. This is just the way I'm going to choose to do this. So this is 30t squared is equal to 80. And I divide by 30. Then what that'll do is that'll give t to the second is equal to 8/3. If you do that, then you got to do square root of both sides. So you get t equals plus or minus the square root of 8/3. And since time is always positive, we'll get time is equal to square root of 8/3. And I'm not going to get a decimal. I'm just going to kind of do that for now. All right, now I'm going to move this graph, just cut that, erase a few things. And then we got one more thing to do. Okay, well, the question was, how far has the plane traveled? Well, S of t is giving you how far. S of t we got as this. We did this in the previous problem. We got 480t minus 10t to the third like that. So what we have to do is we have to do S of square root of 8/3. So we're going to do S of square root of 8/3 just by evaluating this function. And we're going to get an exact answer on this. So, don't be lazy about this kind of stuff. You want to never forget how to deal with radicals and stuff like that. Okay, so I've got 480 times the square root of 8/3 minus 10 times the square root of 8/3 to the third power. Okay, so I'm just going to kind of work all this stuff out here and see where this leads us then and try to simplify it. All right. Okay, I just thought of something. I paused for a minute. I think you could work this out, but you know what would be better? Would be you can factor. I think this thing's easier to work out if you take out common factors. So I'm going to go ahead and do that. The common factor between 10 and 480 is 10. Your common factor here is root 8/3 to the first and the third, so you just take this out. Okay, that's a common factor. You would end up with 48 minus square root of 8/3 to the second power. Let me write that a little bit neater. You don't have to do it this way, but I think it'll make it easier because we want to get an exact answer. One of the things you're going to get into with integrals is you're going to do a lot of this arithmetic from time to time. Okay, so I've got this then. Okay, so I'll write the factoring that way then. Okay, let's see. Am I right? I think I'm okay. And let's see. That was to the second power. Okay, so I took a 10 out. I took a root 8/3 out, so 10 times 48 is 480, and then that's right. Okay, so here's what I have. I'm going to write down the 10 root 8/3 times 48. What happens when I square a radical? Radical comes off, so I'm down to that point right there then. Okay, so I'm going to put that over 1. I'm going to get a common denominator, so I'll have 10 times root 8/3 times 48 over 1. I got a common denominator of 3, so I need to multiply this by 3 over 3. Okay, like that. All right, and I'm just going to do this. This is 10 root 8/3. And then this will be, let's see, 48 times 3, I think is 14. Hold on just a second. Okay, just had to take care of something. Okay, so I'm back. Okay, so just finishing up the arithmetic. Then we got 48 times 3, 144. So this becomes 144 over 3 minus 8/3. Okay, and then this is going to become 10. I'm going to go ahead and break this down now. So I've got square root of 8, I'm going to break down into 4 times 2. I'm going to leave the square root of 3 the way it is. 144 minus 8, we're going to work that out. So that's 136 over 3. Okay, like this. Okay, just hang in there with me because I want to run through some of this arithmetic when we do this. So now I've got 10 square root of 4 is 2. Whoops, it's going to be a 2. This is going to be 2 root 2. You can probably do that in your head. So the square root of 8 is 2 root 2. Got square root of 3. Then I'm going to rationalize this denominator. So I'm going to multiply by 3, square root of 3 over 3. And then I'm going to multiply by the 136 over 3. All right, so here's what I get. I get 10 times 2 is 20. So I've got 20 times 136. So that will be 2,720. Square root of 2 times square root of 3 is square root of 6. Okay, and then what I have here is, this is really the denominator. Square root of 3 times square root of 3 is 3. So we have 3 times 3, so we have 9. That's your exact answer to the problem. Okay, I think if you do a decimal on that, that will give 740.29 miles. Okay, so that's the answer. Okay, and you know, this arithmetic on here gets hairy sometimes if you want to get exact answers, particularly if you got radicals and stuff like that. You can use your calculator to help you with certain parts of that, though. Okay, so one last thing to wrap us up. Let's see. We can get velocity from acceleration. And this is, I'm not going to spend a lot of time on this because it's the same idea. The idea is you learn that the acceleration is the derivative of the velocity. So hopefully this will make sense to you. If your a of t is v of t, so these integrals are equal. If you do the integral of the acceleration, that's the same as doing the integral of the derivative of the velocity. And then the antiderivative of the derivative, v prime, gives you v. So that gives you this. So you end up having a formula here. So you end up really having, this is what I want to point you to. You want to look at those two things right there and look at how this theorem is developed. So what we have then is, if you move this over, you end up getting just kind of general v of t, and then you get an initial velocity. So this is very similar to what we did with the other formula a minute ago. So this is how you can find velocity from acceleration. Okay, so you do the integral of the acceleration, and then you look at the initial velocity like that. Okay, this is real similar idea, okay, to how you can find a position from the velocity. Okay, so this is analogous to this formula right here. This is how you get position from velocity. So if you just change everything, you would have v of t is v of 0 plus the integral 0 to t of a of x. Okay, so it's the same idea exactly. Okay, so I'm not going to spend much time on that because it's a similar idea. Okay, so on this one, what we're going to do is find the position and velocity of an object moving along a straight line with this given acceleration. Those of you who know about physics, that's negative 9.8 meters per second squared. Acceleration due to gravity. Initial velocity is 20. Initial position is 0. So we're going to use this formula. We're going to do this in a couple steps. First thing we're going to do is find the velocity. Okay. So the velocity, we're going to do it this way. I'm just going to choose to do it this way. What we do is we do the integral of the acceleration to begin with. So that means the velocity is going to be the integral of negative 9.8 dt. So that means the velocity in general is going to be negative 9.8 t plus C. Okay, now we can find C because we have this initial condition. See, that right there gives us a point, 0, 20. So that means the velocity is 20 when the time is 0. So so what you do is you just find 0 that way. So that would be 20 equals negative 9.8 times 0 plus C. Therefore, C is 20. Okay, so therefore we end up with this. V of t is just equal to negative 9.8. T, you don't need the plus C, I'm sorry, the C is equal to 20. Okay, so that's the first thing is we have the velocity. Okay, so we just integrate the acceleration, use the initial condition to find the constant C. Okay, so that's the first thing. Second thing we're going to do is we're going to find S of t. So S of t, we know, is the integral of the velocity, which we have that function. So S of t is going to be the integral of 9.8t plus 20t times dt. Okay, so we do that. That will be negative 9.8t to the second over 2 plus, hold on. I made a mistake there. That's 20. A little sloppy there. Okay, so that would be 20t like that plus c. All right. Okay, so if we put this together then we can use that initial condition to figure this out then. Okay, because we're trying to find that position then. Okay, so let's see. You can divide that by 2 if you want to. Just simplify that. 9.8 divided by 2 is what? 4.9. So that is negative 4.9 t squared plus 20t plus c. Okay, so that's S of t. And then we're going to use this condition, S of 0 equals 0. That just means that the position is 0 when the time is 0. That you can do in your head. C is just going to be 0 if you solve that equation. So therefore, the result you get is this. You get S of t is equal to negative 4.9 t squared plus 20t. All right, so that would be the answer on that. So you have enough information on that. If you're given an acceleration, you're given an initial velocity and an initial position, you can build the position function and the velocity function. Okay. One thing I want to point out on here real quick is notice if you do the derivative of this function, you get this. So the derivative of this function is the velocity. And if you do the derivative of the velocity, you get negative 9.8. So you can kind of work backwards to that problem and tell that you're correct. Okay. All right. So that's a lot of information on that section. I tried to go through that real thoroughly. One suggestion that I want to make, just if you want to, is I always give you the solutions to my notes. So a good thing that you might think about doing as you're watching these videos, just print out my solutions and write down little notes. You don't have to write down everything, but just write down, put your notes that you need to write to yourself as I'm going through these things. Real important you look at these videos. I mean, unless you just have a great background, I just think you miss a lot of things if you don't spend some time going through this. You can kind of look at my solutions though, and if there's things on there that you feel comfortable with, you can, bypass that part of the video. So use this intelligently and make sure that you know all these examples and concepts I go over. All right, I'll get this posted. Have a great day and good luck.